So anyway, as you as you know, anyway, let me start by reminding the way the defense will be conducted, right? So G will first present his, give a talk, right? That will last about 45 minutes or so, right? Approximately. So the talk will be followed by a session of public questions. If anybody in the audience has questions, is welcome to ask questions. This includes students who are present here, as well as also the committee members. So this will be followed by a closed discussion, which will be limited to G and the committee members, where we can go deeper into the topic of the research, right? After which, we will give our evaluation, right? Anyway, so as you know, G we work with me for this is the 5th year now, right?
Yes.
So we've been working on different topics, and in fact, the thesis covers essentially the talk covers one part, still a significant part of what we did together. So the title is about approximations of functions of smooth manifold using neural networks. So I leave the podium to G.
Thank you.
With your
Thank you, Dr. Nafati, for the kind introduction. Thank you. Good morning, everyone. Thank you for attending my PhD defense. I'm honored to present the findings of my PhD studies. The title is Optimal Approximation of High-Dimensional Functions on Smooth Manifolds using the Deep Neural Networks. First, I want to thank my advisor, Dr. Nafati, for introducing me to this fascinating research field and for his continuous support. I also want to thank my committee members, Dr. Eisenkot, Dr. Kagadaris, and Dr. Mang for their invaluable time and for their insightful feedback on my dissertation. Okay, before introducing my research results, I would like to.
So Jay, let me interrupt you. You may want to turn your camera to you rather than we see the thing, but we want to see you.
Now it's okay?
Yes.
Okay, before introducing my research results, I would like to introduce the background and the significance of my research. As we know, the deeper neural networks have achieved great success.
No, you can stay there. I will orient you. Yes.
Achieved great success in many applications, particularly in dealing high dimensional data. Now, its question is why deep neural networks work well in high dimensional space. My research aims to provide the part of explanations for this phenomenon. My presentation has the 4 parts. First part, I will give a brief introduction to neural networks, such as notations and definitions. In the second part, I will review some classical results in the neural network approximations and present our latest results. Third part is our main part. I will talk about the dimensionality reduction using the deep neural networks and present our latest results. In final part, I will give some remarks. Let's move on to the first part, neural networks. Some people describe the neural network as a black box. That is, neural network is an algorithm for processing an input acting on capital D and returning an output in a little k. So this black box has 2 steps. Just this process alternates between the 2 simple steps. First is the affine linear transformation, just this AX plus B. Second step is the nonlinear activation function rho applied coordinate-wise. So unlike traditional signal processing that relies on linear superposition, Neural networks are defined by functional combination. Okay, let's say a simple situation. Shallow neural network. Neural network with only one hidden layer, just this, one hidden layer. The layer between the input and the output layers is called the hidden layer. So with only one hidden layer is called the shallow neural network. The following is its expression. First, we apply linear map. This is affine linear transformation, followed by nonlinear activation function, followed by another linear map. So this is the shallow neural network. Let's say a deep neural network. A deep neural network has multiple hidden layers. The following is its expression. Here, the W is the affine linear transformation is W of x equals to ax plus b. The A is we call A the filter. This P we call this bias. Here actually A is a matrix. The B is a vector. This rho is activation function. I will give some introduction to notations. For example, this L is the number of the layers of the neural network. And the depth, what is the depth? The depth is the number of hidden layers, equals L minus 1. N sub L is the width of the L's layer. This capital N is the width of neural network. What is the width of neural network? This width is the maximum width of all hidden layers. Later I will give example. The last notation is the W of phi is the number of the non-zero width of neural network phi. Let's see an example. This is the 4-layer neural network. This is, you can see the first layer, second, third, fourth. 1, 2, 3, 4. This is the number of the layers equal to 4. The depth is the number of the hidden layers. 1, 2, 3 equal to 3. What is the width of the neural network? You can say the width is the maximum width of all hidden layers. You can say the first hidden layer 4, second 4, third 4. Takes a maximum value equal to 4. This is the width of the neural network. Okay, the following, the number of the weights equals the 57. This is its expression. As we know, there are many different activation functions. Here, I will give the 2 examples. First is sigmoid function, rho of x equal to 1 over 1 plus e to minus x. Second is rectified linear unit function. We call the random function, rho of x equal to the maximum of x and 0. The following are their graphs. As we know, the ReLU is the most common activation function in deep neural networks. Okay, in our research, we do identify a neural network as a function. The following I will give a special function class. This F calligraphic F of W naught, L naught, B naught denotes function class from neural networks. This neural network, the weight of the number of the weights bounded by W naught, the number of the layers bounded by L naught, the scale of this neural network bounded by B naught. What is the scale? The scale is the maximum value of all parameters in this neural network. Okay, now we have constructed this function class or the neural network class that we can train the data. The given data S consists of xi, f star of xi. Each XR follows the distribution mu. Now we want to training this data to get a hypothesis function from this data. This hypothesis function space is a neural network class. Now there are the 3 steps to learn this hypothesis function. The first step is to construct a hypothesis space, just a neural network class. This is a neural network class. The second step is to design a loss function. The third step is to minimize the empirical risk. Now you can see this picture. This is the best model in our hypothesis space. Best model. Now, how do we get this best model? We need to compute the population risk minimizer. Is F tilde. But we can't do this because for a population risk, we need to know the distribution of the data. In true data, we don't know the distribution of this data, so we can't do this. Instead, we compute the empirical risk minimizer, just the F bar. But we also can't do this step, just because due to the limitation of current optimization method, we just can get a numerical solution of empirical risk minimizer, just the F hat. This is our learned model in this hypothesis space. This is our target function F star. The distance between these 2 functions, F hat and F star, bounded by 3 arrows. You can see bounded by 3 arrows. First arrow is approximation arrow. The second is optimization arrow. The third is generalization arrow. So today I will focus on the approximation arrow. That is the distance between the best model in our hypothesis space and the target function. So this approximation theory is to study the expressive power of the neural network. Let's move on to the second part. In this part, I will review some classical results and present our latest result. First, I will introduce a universal approximator. In 1980s, universal approximation theorems are used as a justification for expressive power of the neural network. The following definition is give a function class is called a universal approximator of a compact set S. If for every continuous function G and target accuracy epsilon, we can find a function F in this function class. To approximate this continuous function G with the uniform approximation error bounded by epsilon, we call this function class universal approximator. Typically, we choose this compact set S equals 0, 1 capital D, unit Q. There is a classical result. The classical Weierstrass theorem states that polynomials are universal approximators. Harnik, 1989, also shows that the shallow neural network with a C, this is the activation function, with a C infinity non-polynomial activation function are universal approximators. So this means shallow neural networks are universal approximators. Now the question is, if shallow neural network can approximate everything, why we care about deep neural networks? The following result gives the answer. The Tarkovsky from 2016 states that the approximation obtained by by deep neural network cannot be achieved by only shallow neural networks. Unless the number of the neurons in this shallow neural network grows exponentially. So this result shows that the deep neural network can improve the expressive power. Okay, next I will introduce our latest results using the deep neural networks. First, I want to review two function classes. First function class is as times continuous differentiable function. We denote with the CS of the 0, 1, capital D. In our research, we just consider the closed ball in this space with the radius m. This is consisting of the function whose norm bounded by m. The following is the definition of a norm. You can see this is the definition of the norm. Next, I will introduce another function class is the Hodak continuous function space. This function first, if this function in this Hodak continuous function space, first this function should be the floor of alpha times continuously differentiable function. We give the following definition of the norm. The first is same as the above norm. The second part we add the Lipschitz constant. We also care about the closed ball in this space with a radius lambda. The consisting of the function whose norm bounded by lambda. If a function in this space, we call this function is the alpha smooth Hodak continuous function with the Hodak constant lambda. So next this is our first result. Our first result states that the target function is the alpha smooth Hodak continuous function with Hodak constant lambda. You need to notice this the smoothness alpha is 0, 1. We can find a deep neural network phi with the width capital N and the depth L to approximate this target function with the uniform approximation error bounded this type of estimate. The following is the complexity of deep neural networks. Is the W equals the order of epsilon and to capital D of alpha. So our result, in our result, our approximation rate is this term is the optimal, and our constant C is explicit, improving the following results. The C in the following results is implicit. You can see our constant is explicit. We improve the following result. Next, this is our second result. We consider the target function is f naught is the s times continuously differentiable function. But you need to keep in mind that this s is a natural number. So we also can find a deep neural network with the width n depth L to approximate this target function f naught with the uniform approximation error bounded this type of estimate. Our approximation rate is optimal, and our constant C is explicit with the polynomial dependence on the capital D. How to approve this approximation rate is optimal. We just use the VC dimension theory to prove this is the optimal. our results improves the previous results, including the Peterson, the Lu, and the Job. Their results, first, their result, the C depends on the D exponentially instead of polynomially. The second, our approximation rate is the best now. It's the first result because their results just n square L square. No, this log-term. We add this log-term. This is the optimal result among all existing results. Okay, but you need to. Here I will give the remark. You can see, although our result is the optimal, but this complexity of the neural network still suffers from curse of dimensionality phenomenon. You can see here the number of the weights grow exponentially with this input dimension capital D. So let's move on to third part. I will talk about the dimensionality reduction using deep random neural networks. So you can see the above section, we know our result, although our result is optimal, but the deep neural networks still suffers from curse of dimensionality. This means the success of deep neural networks in applications is not fully understood by their mere approximation properties. So their performance in many problems with very high input dimensions appears to overcome the curse of dimensionality. Now the question is, what is the curse of dimensionality? What is the definition of curse of dimensionality? The Bellman 1952 states that approximation methods deteriorate exponentially faster with increasing dimension capital D. This is well known in many applications. For example, numerical PDE. If you want to achieve the epsilon accuracy, the number of the weights will grow with the rate of the epsilon to minus capital D. This will suffer from the curse of dimensionality. So now I will give some observations. In many multi-dimensional problems, data is highly structured, and the information of the interest is low-dimensional. Here I will give an interesting definition about the intrinsic dimensionality. The minimum number of the coordinates necessary to describe a date size point without significant information loss. There are many ideas proposed to infer this intrinsic dimensionality. The following are these ideas. So here we give two observations in classical dataset. MNIST consists of images of the size 28 by 28. This means the ambient dimension of this image, each image, is 784. However, its intrinsic dimension is between 8 and 13. Another example is ImageNet. ImageNet consists of RGB images of the size 224 by 224 by 3, which means the ambient dimension of each image is about 150,000. It's very high, very large. However, its intrinsic dimension is between 26 and 43. So from above observations, we can give the manifold assumptions. It's a manifold hypothesis. The manifold hypothesis is a widely accepted idea in data science. For example, the Keaton from the 2005 states that the dimensionality of many data sets is only artificially high. Although each data point consists of perhaps thousands of the features, it may be described as a function of the only few underlying parameters. That is, the data points are actually samples from a low-dimensional manifold that is embedded in high-dimensional space. With this manifold hypothesis idea, if we want to approximate a function from the manifold to R, this manifold is contained in R capital D. Using this manifold hypothesis, we are not thinking to approximate this target function f with respect to a norm on R capital D. That is the ambient space. Instead, we approximate this target function f on d-dimensional, little d-dimensional manifold M, where the d may be much smaller than capital D. In our research, the capital D is the ambient space. Just this is ambient space. Little d is the manifold dimension. Okay, next I will introduce a seminal result on the manifold hypothesis by the Sham, Koenig, Koipman in 2018. This result shows that M be a smooth, compact d-dimensional manifold, and the target function is still alpha smooth, hold a continuous function with hold a constant lambda. We can find a deep random neural network to approximate this target function f0 with uniform approximation error bounded by this type of estimate. The following is the complexity of this deep random neural network. You can see here, this is the weight of the neural network, W. This complexity grows like the epsilon to minus little d of alpha. Before, this is the capital D, now become little d. But there is a problem, is the C tilde is depends on capital D. In Sham's paper, this C tilde is we don't know. They just say this C tilde depends on capital D. It's implicit. Then Schmidt, Haber, Nakada, Imazumi improve their result. Just say this C tilde depends on capital D polynomially. In our later result, we improve this result. Our C tilde not depends on capital D, just depends on the manifold dimension. There are the two methods and the manifold hypothesis. First is the non-constructive method, and that is to use appropriate version of the Johnson-Ingstrom lemma to project the high-dimensional data to the low-dimensional space. That is using random matrix A. The second method is constructive method. Constructive method is to construct an explicit chart to project the high-dimensional data, project the data on the manifold to low-dimensional space. Note just in this picture. Okay, first I will introduce our first result. We use non-constructive method to get the following result. This theorem says that the manifold M be a compact Riemann d-dimensional manifold, and the target function f0 is still alpha alpha smooth hold a continuous function with constant hold a constant lambda. But here the smoothness alpha is 0, 1, just 0, 1, less than 1, because there is no well-defined definition for this hold a continuous function on manifold. We can find here the DE is effective dimension is between the manifold dimension and the ambient dimension. But this DE just depends on the manifold dimension, little d. We can find deep random neural networks this set to approximate this target function f0 with uniform approximation error bounded by this type of estimate. The following is the complexity of this deep random neural networks. Okay, you can see here the complexity of this deep random neural networks grows like the epsilon to d sub e of alpha. This is the DE instead of the capital D. The DE, we know the DE just depends on the manifold dimension little d. The C2 we improve the previous result. C2 doesn't depend on the capital D, just depends on the d sub e. But here I will give a remark. The W is the number of the weights in the hidden layers instead of the weights of the weights all layers. We didn't consider the input layer because the input layer always includes the dimension capital D. So we didn't consider the input layer. Okay, our result improves the existing results like the Tsai, Zhou, and Kalik. Their result, the constant C2 in the following results still depends on capital D. Okay, I will introduce the key idea in our approach in this slide. Our approach is to use appropriate version of the Johnson-Lingstrom lemma. Let's first quickly review this classical Johnson-Lingstrom lemma from the 1984. This lemma states that the distortion delta in 0, 1, x1 up to xp in R capital D be arbitrary points. This M, no dimension M, depends on distortion parameter and the number of the samples. We can find a Lipschitz map F. This map F have the following asymmetric property. This map can preserve the distance from the high dimensional space to low dimensional space. Okay, in order to prove our result, we need to extend the classical Johnson-Lingstrom lemma to the manifold. This is our version of Johnson-Lingstrom lemma. The first part we give some technical assumptions about the manifold on the manifold. These technical assumptions on the manifold constrain its curvature. Second part is delta is the distortion parameter in 0, 1/3. The A is a random matrix. Each element in this random matrix A follows the following distribution. The low dimension D delta just depends on the distortion parameter, and you can say the little d is manifold dimension. Not depends on ambient dimension capital D. So with the high probability to get the following asymmetric property. Okay, now I will explain what is the delta. What is the delta? Next slide, I will introduce what is the delta. The delta in 0, 1/3 can trace the trade-off of the isometry and dimension reduction. The delta close to 1/3, d delta close to manifold dimension little d. But we just can get a weak asymmetric property. If this delta close to 0, this d delta farther from the manifold dimension little d. However, we can get the bad asymmetric property. In our argument, we took the delta equal to 1/3. This means the effective dimension equal to d sub e equal to d 1/3 in our result. Okay, with this version of the Janssen-Ling's lemma and the manifold, we can prove our result. This is the main idea of our non-constructive approximation result. This is the target function. F0 is the alpha smooth Hölder continuous function. We define a low-dimensional function G0 on the 0, 1 to d sub e by projecting this target function F0 to using the following the Poisson, this affine map. The A in this affine map Poisson, the A is a random matrix. Use our version of the Janssen-Ling's lemma and the manifold. The second step, we construct a neural network to approximate this low-dimensional function G0. The third step is to combine the above the neural network and this affine map Poisson. This Poisson is easy to construct a neural network to realize it. Combine these two neural networks to get the final neural network phi to F0. We can use this neural network to approximate the target function F0. There are some challenges. First is to ensure the projected the function G0 is Hölder continuous.